Welcome, cosmic explorers, to a mind-bending journey into one of the universe's greatest mysteries. Today, we're diving deep into the enigma of dark matter, the invisible force shaping galaxies and the very structure of the cosmos. You can't see it, you can't touch it, yet it's all around us, silently guiding the dance of stars and galaxies across billions of years. What is dark matter? How do we know it's there? And why does it hold the key to unlocking the secrets of the universe? Buckle up, because we're about to embark on an epic adventure that will stretch your imagination and leave you hungry for more. Let's unravel the mystery of dark matter together. Picture the night sky, a tapestry of twinkling stars, swirling galaxies, and vast cosmic clouds. Now, imagine that everything you see, every star, planet, and speck of light, makes up just a tiny fraction of the universe. Scientists estimate that ordinary matter, the stuff we're made of, accounts for only about 5% of the cosmos. So, what's the rest? Roughly 27% is dark matter, an elusive, invisible substance that doesn't glow, reflect light, or interact with it in any familiar way. Yet, its gravitational pull shapes the universe on the grandest scales. The remaining 68%. That's dark energy, a mysterious force driving the universe's expansion, but that's a story for another day. Today, our focus is dark matter, the unseen architect of galaxies. Doesn't that make you wonder what's hiding out there, just beyond our senses? Let's start with the origin of this cosmic puzzle. The idea of dark matter first emerged in the 1930s, thanks to a Swiss astronomer named Fritz Zwicky. While studying the Coma cluster, a group of galaxies 300 million light-years away, Zwicky noticed something odd. The galaxies were moving so fast that, by the laws of gravity, the cluster should have flown apart. Yet, it held together. Zwicky calculated the mass needed to keep these galaxies in orbit and found the visible stars and gas fell far short. He proposed an invisible, missing mass, which he called Dunkelmaterie, or dark matter, was at work, providing the extra gravity to bind the cluster. At the time, his idea was bold, even controversial, but it planted a seed. How could something we can't see wield such power over the cosmos? Fast forward to the 1970s, and another brilliant mind, American astronomer Vera Rubin, brought dark matter into the spotlight. Rubin studied the rotation of spiral galaxies like Andromeda. She expected stars at the galaxy's edge to move slower than those near the center, just as planets orbit the Sun more slowly the farther out they are. But her observations, made with precise measurements of star speeds, revealed a shock: stars at the edges moved just as fast as those near the core. This defied Newton's and Einstein's laws of gravity unless extra, unseen mass was present, boosting the gravitational pull. Rubin's work suggested galaxies are embedded in vast halos of dark matter, extending far beyond their visible edges. Her discovery was a game-changer, and it's thanks to pioneers like Zwicky and Rubin that we began to grasp dark matter's invisible grip. Isn't it wild to think galaxies owe their shape to something we can't even see? So, what exactly is dark matter? Here's the catch: we don't fully know. Scientists define it by what it isn't. It doesn't emit, absorb, or reflect light, making it invisible to telescopes. It doesn't interact with electromagnetic forces, so it ignores light, radio waves, and X-rays. But it does exert gravity, bending the paths of stars and even light itself. This clues us into its presence. Researchers have proposed many candidates for dark matter. One leading idea is weakly interacting massive particles, or WIMPs, hypothetical particles that barely interact with normal matter except through gravity and perhaps the weak nuclear force. Other possibilities include axions, ultralight particles theorized to solve problems in particle physics, or even sterile neutrinos, elusive cousins of the neutrinos we know. Some wonder if dark matter isn't particles at all, but a flaw in our understanding of gravity. The mystery is deep, and that's what makes it so thrilling. Let's explore the evidence, because science thrives on proof, not guesses. Beyond galaxy rotation and cluster dynamics, dark matter leaves its mark in other stunning ways. One of the most beautiful is gravitational lensing, a prediction of Einstein's general relativity. Massive objects, like galaxies or clusters, warp spacetime, bending the light from objects behind them. In the 1980s, astronomers observed distorted arcs of light from distant galaxies, bent by the gravity of unseen mass. The amount of bending revealed far more mass than the visible stars and gas could account for, dark matter again. A famous example is the Bullet Cluster, where two galaxy clusters collided a billion years ago. X-ray images show hot gas clashing, but gravitational lensing maps reveal most of the mass, dark matter, passed through, untouched, proving it's distinct from ordinary matter. Doesn't that image of invisible mass bending light spark your curiosity? Another clue comes from the universe's baby picture, the cosmic microwave background, or CMB. This faint glow, discovered in 1965, is the leftover heat from the Big Bang, dating back 13.8 billion years. Satellites like COBE, WMAP, and the Planck spacecraft map tiny temperature variations in the CMB, ripples from the early universe. These fluctuations show how matter clumped together to form galaxies, but the patterns only make sense if dark matter was present early on, providing the gravitational scaffolding for structure to grow. Without dark matter, galaxies, stars, and even us might not exist. The CMB is like a cosmic fingerprint, and dark matter's signature is all over it. How amazing is it that an invisible force helped build the universe we see? Let's dive into dark matter's role in shaping galaxies. In the early universe, after the Big Bang, matter was a hot, chaotic soup. As the cosmos expanded and cooled, tiny density variations appeared. Dark matter, immune to the radiation and pressure that scattered ordinary matter, began to clump under gravity, forming dense pockets. These became the seeds of structure, pulling in gas and dust to ignite the first stars and galaxies. Computer simulations, like those from the Millennium Run or Illustris project, show this beautifully. Without dark matter, galaxies would be too spread out, too slow to form. Instead, dark matter halos, vast, spherical clouds, envelop galaxies, holding them together and guiding their growth. Our Milky Way likely sits in a halo hundreds of thousands of light-years wide, with dark matter outweighing visible matter by 5 or 6 to 1. Imagine that, an invisible scaffold shaping the cosmic web. Speaking of the cosmic web, dark matter doesn't just sculpt individual galaxies, it weaves the universe's grand architecture. Astronomers map the cosmos and see galaxies arranged in filaments, walls, and clusters, separated by vast voids. This structure, spanning billions of light-years, emerged because dark matter's gravity drew matter into threads and sheets, like a cosmic spider web. Surveys like the Sloan Digital Sky Survey reveal this pattern, and simulations match it only when dark matter is included. It's as if dark matter laid the foundation, and galaxies built homes on top. Some clusters, like the Virgo cluster, contain thousands of galaxies, held together by dark matter's pull. Doesn't it blow your mind that an invisible force choreographs the universe on such a massive scale? Now, let's explore how we hunt for dark matter, because the chase is as exciting as the mystery. Since it doesn't emit light, direct detection is tricky. Scientists build ultra-sensitive experiments deep underground, like the Large Underground Xenon, or LUX, and its successor, LUX Zeppelin. These use tanks of liquid xenon, shielded from cosmic rays, to catch rare collisions between WIMPs and atoms. A tiny flash of light or energy could signal dark matter. So far, no definitive hit, but the search tightens the possibilities. Other efforts look for indirect signs. If WIMPs collide and annihilate, they might produce gamma rays or particles detectable by telescopes like the Fermi Gamma-Ray Space Telescope. Scientists also study particle accelerators, like the Large Hadron Collider, hoping to create dark matter in high-energy collisions. Each experiment brings us closer, but the quarry remains elusive. What do you think we'll find first? Let's consider alternative theories, because science loves a challenge. Most researchers favor particle-based dark matter, but some question if gravity itself needs a tweak. Modified Newtonian dynamics, or MOND, suggests gravity behaves differently on large scales, mimicking dark matter's effects without needing it. Another idea, modified gravity, adjusts Einstein's relativity to explain galaxy rotation and lensing. These theories have followers, but they struggle to match all evidence, like the CMB or the bullet cluster, where dark matter separates from normal matter. Most cosmologists stick with dark matter, but these debates keep us sharp, pushing us to test every angle. The universe loves to keep us guessing, doesn't it? What about dark matter's cosmic cousins? It's tied to dark energy, that mysterious force accelerating the universe's expansion. Together, they make up 95% of the cosmos, dwarfing the ordinary matter we know. Dark matter pulls things together, while dark energy pushes them apart, a cosmic tug-of-war shaping our universe's past and future. In the early universe, dark matter dominated, building structure. Today, dark energy drives galaxies apart faster and faster, hinting at a cold, sparse future, sometimes called the Big Freeze. Some wonder if dark matter and dark energy are linked, perhaps tied to a deeper theory of everything. Quantum gravity, string theory, or other ideas might unify them, but we're still searching. These mysteries fuel our quest, don't they? Let's zoom in on dark matter and our galaxy. The Milky Way, our cosmic home, spins with stars, gas, and dust, but its rotation speed, hundreds of kilometers per second, demands more mass than we see. Dark matter's halo, perhaps 10 times the mass of visible matter, keeps it stable. Some think dark matter particles stream through Earth, even through us, every second, unnoticed because they barely interact. Telescopes hunt for signs, while simulations model how the halo shapes our galaxy's spiral arms and star formation. Dark matter might even influence the odds of life, by stabilizing galaxies long enough for stars and planets to form. You and I, we're part of a story written by this invisible force. Now, let's tackle some myths. Dark matter isn't a black hole. Black holes are dense, collapsed objects, while dark matter is spread out, diffuse. It's not antimatter, which annihilates normal matter in a flash of energy. Dark matter just sits there, gravitationally quiet. And no, it's not science fiction. The evidence, rotation curves, lensing, the CMB, is rock solid. Some wonder if dark matter hides alien tech or cosmic secrets, but science sticks to what we can test. The real story is thrilling enough, an invisible substance, shaping the universe, waiting for us to crack its code. Doesn't that fire up your imagination? How do we study dark matter today? Astronomers use telescopes across the spectrum, optical, X-ray, gamma-ray, to map its effects. The Vera C. Rubin Observatory, set to scan the sky soon, will track billions of galaxies, tracing dark matter's influence through lensing and motion. Gravitational wave detectors, like LIGO, might spot ripples from exotic dark matter objects. Underground labs, particle colliders, and computer models work together, piecing the puzzle. Each step refines our picture, but dark matter keeps some tricks up its sleeve. Future missions, like the Euclid satellite, will probe deeper, mapping the cosmic web with precision. The hunt is on, and it's a cosmic detective story. What does dark matter mean for the universe's fate? Early on, it built the scaffolding for galaxies. Today, as dark energy speeds up expansion, dark matter's pull still holds clusters together. Billions of years from now, galaxies may drift apart, stars burn out, and the cosmos grows cold. Dark matter will linger, a ghostly presence in a sparse universe. But could it hold surprises? Some theorize exotic forms of dark matter, like self-interacting particles, might change its role. Others wonder if it ties to a grand theory, blending gravity, quantum mechanics, and the cosmos. The questions are endless, and that's the thrill. Let's reflect on the human side. Dark matter's story is our story, a testament to curiosity. From ancient stargazers to modern physicists, we've wondered about the unseen. Zwicky and Rubin dared to imagine beyond the visible, and today, thousands of scientists chase this mystery. It challenges our tools, our theories, even our sense of reality. Yet, it connects us to the cosmos. The atoms in your body, forged in stars, owe their home to dark matter's gravity. We're part of this grand, invisible dance, and our quest to understand it drives us forward. Isn't that humbling and exciting? As we near the end, let's gaze ahead. Dark matter remains a cosmic enigma, but each discovery, lensing, rotation, the CMB, brings us closer. New telescopes, detectors, and theories will push the boundaries, hunting for particles, testing gravity, and mapping the universe. Could dark matter unlock the nature of reality? Might it reveal new physics, new realms? The journey is far from over, and you're part of it. What questions does dark matter spark in your mind? How will we solve this cosmic riddle? Thank you for joining me on this epic dive into dark matter, the invisible force shaping galaxies. I hope your curiosity is ablaze. If you love this cosmic adventure, hit that like button, subscribe, and ring the bell for more journeys into the unknown. Drop your thoughts in the comments. What blows your mind about dark matter? What mystery should we explore next? Until then, keep looking up, keep wondering, and let's unravel the universe together. See you in the next video, Cosmic Explorers.